would like to begin a discussion with you on intermolecular forces of attraction. But before I do that, I want to ask you to remember when we began our discussion of chemistry that we discussed how matter can exist in either the solid, the liquid, or the gaseous state. We, of course, have observed this. And we examined and described that matter in both the solid and liquid states, the particles that make up the matter are in very close contact with each other. Liquid particles possess sufficient kinetic energy so that they can actually move and slide around each other, which explains why liquids are fluids and assume the shape of their container. Solids, on the other hand, in close contact, but the particles held in fixed positions relative to each other. So solids have a definite shape as well as a definite volume. Both liquids and solids in close contact, but it's understanding whether or not their particles are free to slide around and move past each other that help us understand whether or not they have a fixed shape as solids do, or a non-definite shape of fluid state as liquids are. Gases, on the other hand, we remember the particles that make up gas state very far apart from each other. We know that gas molecules or particles are moving very fast. They can collide together, but when they do, there's no observed tendency for the gas molecules or atoms to stick together and remain in close contact. If they did, then they would reform or transfer to either the liquid state or, if cooled down enough, to the solid state. So you need to remember those properties of solids, liquids, and gases as we look at intermolecular forces of attraction. Now we're going to be saying this so often and writing it that I have an abbreviation that's useful and helpful, abbreviating intermolecular forces of attraction as IFAs. This information in Chem 2A is found in Chapter 6 in Section 6.9 and in Chem 22 in Chapter 12 in Section 12.6. So IFAs, intermolecular forces of attraction, what are they? Well, first of all, they're electrostatic forces of attraction. And remember, that's a very big fancy term, which basically means that positive charge and negative charge attract. Right? So all intermolecular forces of attraction are governed by the fact that opposite charge attracts together. So IFAs are electrostatic forces of attraction that operate between molecules and hold them in close contact either as pure substances made up of just one substance in either the liquid or solid state, or as mixtures, a combination of two or more pure substances, but also in the liquid and solid state. So these are the states with which we see that matter is in close contact with each other. Intermolecular forces of attraction determine A, whether a substance will be a solid or a liquid or a gas at any specific temperature. For example, if we're looking at a temperature of 25 degrees Celsius, a very common temperature that scientists like to look and examine the properties of different substances at. If we're at 25 degrees Celsius, all these three substances, substance A, substance B, substance C, at 25 degrees Celsius. But we observe that substance A is a gas, whereas substance B is a liquid, substance C a solid. What conclusions can we make given that all three of these substances at the same temperature are in different phases or states of matter? Well, we can conclude that there are different strengths of intermolecular forces of attraction operating between them. And we can also conclude that as the strength of the intermolecular forces of attraction increase, that favors a substance moving from the gas to the liquid to the solid state. So we would conclude that A has the weakest intermolecular forces of attraction because it is a gas. B, stronger intermolecular forces of attraction than A, because it is a liquid, but C, the strongest intermolecular forces of attraction of all three, because at 25 degrees Celsius, it is in the solid state. So we can conclude that the stronger the intermolecular forces of attraction operating between the molecules of a pure substance, the harder it is to separate those molecules into the gas phase, and the higher the boiling point will be of the substance. The harder it is to separate the molecules and have them form a gas, the greater the temperature, the kinetic energy you will have to give to the substance to convert it into a gas. So the higher the boiling point. So boxing here, greater strength of intermolecular forces of attraction within a substance results in the higher boiling point for the substance. In addition to intermolecular forces of attraction determining whether a substance will be a solid or a liquid or a gas at a given temperature, intermolecular forces of attraction also determine whether two different substances will be soluble in each other. Will they be able to dissolve to form a solution? And we'll be talking more about solutions as we continue on through our chemistry sequence. And you see here that a very common abbreviation for solution is SOL''N, and I'll be using that in subsequent videos. So intermolecular forces of attraction determine whether two different substances will be able to dissolve together and form a solution. So for example, oil does not dissolve in water to form a solution. Why is that? Well, before we address that, maybe I should give you a visual demonstration of what I'm talking about when I refer to intermolecular forces of attraction. These forces that operate to hold molecules together. I have in my hand a Kleenex tissue. And if I try to attach this Kleenex tissue to the board, cause it to stay, it will not. As soon as I let go of the tissue, it's going to fall. And it did. So how could I quite easily cause the tissue paper to stick to the board? And the answer is wet it. Add water to it. So I have some water here in this bottle, and I am making the tissue paper wet. And now I see that the tissue will attach to the board and stay there indefinitely as long as it remains wet. And why is that? Because water has very significant and strong intermolecular forces of attraction operating between the molecules of water. So in short, water likes to stick to other water molecules. And as soon as I get the tissue wet, then the water is on the tissue. It also gets on the board itself. Water has strong intermolecular forces of attraction that cause water molecules to want to stick together. And that attraction holds this tissue in contact with the board as long as there is water present, as long as everything is wet. So taking that visual and going to the example of why is it that oil does not dissolve in water to form a solution. And I know that you have seen this, but it's interesting to demonstrate it here. I have a glass of water, and I am going to pour some oil into the glass of water. So putting the oil in the water and then trying to stir to make a solution. I see that the oil disperses in the water as long as I am stirring and adding energy by the stirring. But as soon as I stop stirring, I observe an immediate separation of the oil from the water. The water is literally squeezing out the oil molecules, and because oil is less dense than water, the oil is floating to the top. But what caused the separation is that there basically is very different types of intermolecular forces of attraction operating between water molecules and between oil molecules. So when you try to form a mixture, there is such a dissimilarity in the intermolecular forces of attraction that the water molecules basically just shove or squeeze out the oil molecules as they find other water molecules and form intermolecular forces of attraction with them. So that is the force that's causing the separation to occur, the lack of solution formation. So oil does not dissolve in water to form a solution because there are very different types of intermolecular forces of attraction operating between oil molecules as a pure substance and between water molecules as a pure substance. But we know that sugar does dissolve in water to form a solution. So here is a second glass of water, and here is some sugar molecules, right? And I'm adding the sugar to the water, and I see that the sugar separates to the bottom of the water, right? No solution has formed yet, but I haven't given it a chance. As soon as I start stirring, I see the solid sugar molecules swirling around, and it's clear to me as I stir that the amount of white sugar crystals that I observe is getting smaller and smaller and smaller to my eye until I see that there is no longer two different substances, water and sugar, but one solution that has been formed by the sugar dissolving in the water. So why is it that sugar can dissolve in water to form a solution? Well, the answer to that ultimately lies in the types of intermolecular forces of attraction found within the pure sugar and within water. Those intermolecular forces of attraction are very similar in nature. Sugar has similar intermolecular forces of attraction operating within it as water does within water molecules. So it's very easy for them to mix together and form a solution. They can attract to each other as a mixture in ways that they can attract similarly to their own molecules as a pure substance. So sugar dissolves in water to form a solution because water and sugar have similar intermolecular forces of attraction. There are different types and relative strengths of intermolecular forces of attraction, as we've already alluded to, and I want to now be specific with you about what they are. So I've listed the types of intermolecular forces of attraction that we will be discussing in the next couple of video clips. The types of intermolecular forces of attraction listed according to relative strength. So note the less than signs here. Dispersion intermolecular forces are the weakest of the intermolecular forces of attraction. Dipole-Dipole IFAs are stronger than dispersion IFAs, but weaker than hydrogen bonding. Hydrogen bonding IFAs are weaker than what we call Ion-Dipole IFAs. And I've put a flag and asterisk by Ion-Dipole IFAs because they are a subset of intermolecular forces of attraction that are limited in their scope and where we observe them. We only see Ion-Dipole IFAs in mixtures, and most relevantly, mixtures of ionic compounds or salts dissolved in water. So Ion-Dipole IFAs are stronger than hydrogen bonding, but they're limited in their application, basically only really relevant for the most part in aqueous solutions of ionic compounds that are soluble in water. The other three types of intermolecular forces of attraction can be found both within a pure substance, operating between molecules that are identical of a pure substance. They can also operate in mixtures, combinations of different pure substances together. Notice that all four types of intermolecular forces of attraction, and you see here the double less than sign, are significantly weaker, much weaker than ionic bonding and covalent bonding. So the last thing I want to stress here in this segment is that intermolecular, emphasis on inter, a prefix that means between. So intermolecular forces operate between molecules to hold them in close contact. Ionic bonding and covalent bonding are not intermolecular. They are not between molecules. They're within molecules or compounds. So I use the term intramolecular loosely. We understand that ionic compounds are not molecules, but the idea here, intra, within, ionic bonding and covalent bonding operate within a molecule or compound to hold it together as a molecule or compound. They do not operate between molecules and compounds. So it's important to note that distinction and the relative strengths. All intermolecular forces of attraction are significantly weaker than the intra, within bonding forces of ionic bonds and covalent bonds.